a related rate problem is really just a word problem in which we're going to look at how some variable, some quantity within our problem changes with respect to time relative to all the other things that are happening within the problem. So we're looking at how something is changing at an instant, at a specific instant in time with respect to time. So really what we're looking at is an instantaneous rate of change of something. And so part of what we'll have to do in each problem is figure out what we're looking for the instantaneous rate of change is. That's kind of our first step, right? Is to read it and understand what's going on in the problem, figuring out which quantity or which variable we are looking for the rate of change of, and which other variables or quantities we might have that we already know the rate of changes of. So that's our first step, figuring out what we're looking for and what we already have. And then we're going to draw a picture, just like we did with optimization, and label it with all the important things from the problem. Being very careful that when we label stuff in a related rate problem, we will only label things that are constants at the beginning. So if I know that an angle is always 30 degrees in the situation of the problem, I can label that angle as 30 degrees. But if that angle is increasing based on something that's happening in the problem, I will not label that angle as a specific numerical degrees or number of radians. I will just label it as, let's say, theta as a variable. If I know that the distance between two things is changing, then I won't label the distance between them as a specific number. It won't be 20, even if that's what it starts at, or if that's what the distance is between them at the point that we're interested in. If that point or if that distance is changing, we'll just label it as d or as x or some variable. Okay? But if the distance between two things is not changing in the problem and it's 20 feet apart, we can label it as 20. Does that make sense?
Yes.
Okay, cool. So once we've done those things, then we just write an equation relating the variables that we know with the variables that we are looking for. And after that, in order to get the instantaneous rate of change of something, we have to take its derivative. And so if we're looking for how something changes with respect to time, we'll have to differentiate both sides of whatever equation we write with respect to time or with respect to t. And so when we do that, we'll have to remember that the other stuff in our equation might be x's or y's or thetas. And if I take the derivative of an x term with respect to t, I have to attach dx dt to it. Or if I take the derivative of a theta term with respect to t, I have to attach a d theta dt to it, right? Or if I take the derivative of a z with respect to t, I have to attach a dz dt to it. Good with that or no?
Yeah.
All right. And we'll talk more about each of these steps as we go through the problems, but just having a basic idea as we go through is a good start. Then we'll just plug in all the crap that we know and get an answer and make sure we put on our units and make sure it makes sense in the context of the problem. All good? Everybody good? Any issues? Any complaints? Everybody feel like you have at least a moderate sense of what we're going to be doing here? Maybe? Let's start with hot air balloon. Everybody likes hot air balloons, right? Unless you're like afraid of heights or something or something. So I'll give you guys a second here to read the question, and then we will work together to do those first couple steps where we write out the things that we know and draw a picture. So take a minute and try and understand what's happening first. All right, everybody have a general sense of what's happening in this problem? Or no? Or did you offer crap reading it and you haven't read it yet? Oh, you do. Okay. All right, so here is a level field. That wasn't very level. That wasn't very level. Pretend that's a level field. I don't like where I drew that. That's nowhere close to level. All right, there's our level field. It's not very level. Here we are. There's us watching a hot air balloon that is rising straight up from a level field. So it's going up, right? I know I didn't draw the basket on the hot air balloon, but you'll survive without the basket on the hot air balloon. Everybody good so far with what we've drawn?
Yes.
Ah, good. All right. So what do we know?
It's 500 feet off the ground.
Is it 500 feet off the ground? And I think that's the 500 is something different, I think. We're tracking it.
Distance from the liftoff point, like it's going straight up, but it's the distance between the point and that other point that you just drew.
These 2 points from where it started to where we are tracking it, that distance is 500 feet, right? And that is not changing whatsoever. Everybody agreed that that would not be changing at all?
Yeah.
Okay, good. Now, what else is happening? It is going up, right? How is it going up? It's going straight up. What does that tell us about this angle here? Should be a right angle.
It's 90.
Yeah, and that angle is not changing, right? The balloon is rising straight up. That angle is 90 degrees forever, right? If it's going straight up. All right, and so we could probably see that this could become a nice little right triangle here. And what are we looking at in terms of things that we want to know? We want to know how fast is the balloon rising at some specific moment, which we'll get to in a second. Well, how fast is rising would be a change in this distance with respect to time, right? How fast something rises, let's say in feet per minute, right? That's a change in distance over a change in time. True? So what should we call this distance between here and here? Do we know what that distance is?
No.
No. So let's call it, since it's in the y direction, let's call it y. Good with that or no?
Yes.
Okay. And so that would then tell us that we want to know how fast y is changing, or what dy dt is. So we're looking for the rate of change with respect to time of y. Everybody good with that being what we're looking for?
Yes.
Okay. What else is given to us in here? Something about the angle, right? Is that angle changing as the balloon rises?
Yes.
So can I label it as a specific angle, a specific number of radians or a specific degree?
No.
Since it's
No.
changing? No, we have to just label it as a variable. So let's call it theta. Now, there is a specific instant that we are interested in. And what instant is that? When theta is
Pi over 4 radian.
pi over 4 radians. And so we're going to write out that the instant we're interested in is when theta equals pi over 4, but we're not going to write pi over 4 in over here. We're going to use theta for any equation that we write. And how is theta changing? With respect to time. What is d theta dt?
It's like the inverse tangent of y over 500.
Well, I just meant in the context of this problem. I mean, you're right about that. We'll get to that in a second. But how is theta changing? It's increasing at a specific rate, isn't it? D theta dt is 0.14 radians per minute. Theta is increasing at 0.14 radians per minute. Would you all agree with that?
Yes.
Okay, so now I want to quickly go back here. Have we understood the problem and figuring out which variable the rate of change we're looking for? And the variable whose rate of change we know? Yeah, we want to find the rate of change of y. We know the rate of change of theta. So we've done step one. Do we draw a picture and label it with important stuff? Yep. All right, so we've done steps 1 and 2. We now need to write an equation. So you were saying that there was an equation. Somebody was giving us an equation to somehow relate theta and y and maybe the 500. What trig function gives us opposite over adjacent?
Tangent.
Yeah, so tangent theta is y over 500. Sorry about that. Had to deal with one of my children for a second. If we solve that for y, we just end up with this, right? 500 tangent theta equals y. Everybody good with that or no?
Yeah, that makes sense.
Okay, so now we'll take the derivative of both sides of this with respect to t, right? We've written our equation. Next is differentiate with respect to t. So when I take the derivative of 500 tangent theta, the derivative of that ought to be 500 secant squared theta. And then we need to multiply it by d theta dt, because we're taking the derivative of a theta term with respect to t. And then we'll say equals dy dt. Good or no? Derivative of
Good.
y with respect to t is dy dt. Yeah. Everyone good or no? All right, so now let's just plug everything in. We know that dy dt is equal to 500 times secant squared of theta. And the theta we're looking at is pi over 4 times d theta dt, which is 0.14. And so what does that end up giving us? What is the secant of pi over 4? Okay, secant is 1 over cosine. So what's the cosine of pi over 4?
Is it 2 for the secant squared by 4?
Yeah. Yeah, secant squared of pi over 4 is 2. So cosine of pi over 4 is root 2 over 2. So if we flip that, that's 2 over root 2, or just root 2. And if we square that, we get 2. So this becomes 500 times 2 times 0.14, which would be 140 feet per minute. Good or no?
Good.
All right. Nobody's got any issues there. Everyone's okay. All right. Let's take a look at another one. I'll give you guys a minute to read through it, and then we'll go from there. So since this distance is changing, we can only label it with a variable. So we'll call that y. What about the distance from the right-angled intersection to where the speeding car is? Is that changing?
Yes.
Yeah.
Yep. And so since that's in the x direction and we can't just give it a numeric value, let's just call it x. All right. And then it also gives us some information about the distance between the two cars, which would be the hypotenuse of this right triangle. It's increasing at 20 miles an hour. So that's clearly changing. So we got to write that with a variable also. We'll call it z. Does that sound good to everybody? Good or no?
Yeah, that's good.
All right. So is there a way that we can relate those three variables together? There should be. What is it?
The Pythagorean theorem.
Pythagorean theorem.
It should be the Pythagorean theorem. So we should be able to write this as x squared plus y squared equals z squared. And then which one are we looking for the rate of change of? We're looking for the speed of the car. That's in the x direction. So we are interested in finding dx dt. Do we know, let's say, dy dt or dz dt?
We know dy dt.
Okay, what's dy dt? That's how fast the police car is going, right?
So
And what would that be? 60?
Yeah.
All right, now let me ask you a question about that real quick. Is this distance y getting larger or getting smaller?
Smaller.
So anytime the distance is getting smaller, its rate of change has to be a negative. So we'll call that negative 60. Everybody good with making that negative 60?
Yeah.
Okay. And what about dz dt?
20?
Exactly, it should be 20. That's given to us. And is there anything else we know? We know that at the instant we're interested in, the y value, the police car, is 0.6 of a mile north. That's all we really know, right? And it also gives us x is 0.8 of a mile, doesn't it? So we know x and y, and we know dy dt and dz dt. We're looking for dx dt. I think we're ready to take the derivative of this Pythagorean theorem with respect to t. What do you guys think?
Yep.
All right, so we should end up with the derivative of x squared, which is 2x, and then dx dt, and then the derivative of y squared, which is 2y, and then dy dt, and then the derivative of z squared, which is 2z, and dz dt. And as we go through and try and plug everything into this, we have x, sorry, it was 0.8. We're looking for dx dt. We have y. We have dy dt. We don't seem to have z, but we do have dz dt. So we seem to be missing the variable for, or the value for z. Luckily, we could go in and do 0.8 squared plus 0.6 squared equals z squared, just to use our Pythagorean theorem, when x is 0.8 and y is 0.6 to figure out what z is. So what does z come out to be if we do that?
One.
1, exactly. So let's put a 1 in there. And we'll note that we could have, if we wanted to, we could have square rooted both sides of this. And that would have just left us with z on this side. And if we took the derivative of just z, we would get dz dt, and there would be no z term at all. So we wouldn't have actually had to solve for that. But then our derivative over here would be way more annoying, right? It'd be x squared plus y squared inside of a square root that we had to take the derivative of. So it'd be like, you know, implicit differentiation using the chain rule. So it's probably easier, just since it was easy enough to find that to be 1, to do it that way. 1.6 dx dt. This becomes minus 72, it looks like, equals 40. And so dx dt ought to be 112 over 1.6, which seems like that ought to go in 70 times. Which tells us that this car is going 70 miles an hour. Which seems like a reasonable amount, yeah. Maybe not. Maybe you shouldn't be going 70, especially if there's a right-angled intersection. You're probably not on the freeway, so you probably shouldn't be going 70. For all of you children that are starting to drive out there or have been driving, don't go 70 through the right-angled intersection. Any questions on that or no? Anybody still paying attention?
Yeah.
Yes.
Yeah.
Okay. All right. All right. We're just going to do one more of these. So this is the last one we're going to do today. Then you guys are going to get some time to just work on the optimization and related rate problems. So take a minute or two, and why don't you guys see if you can get your picture and try to get an equation written and label all your stuff out on the side for this one. I'll give you maybe 3 to 4 minutes. See how much you can
Is
get.
conical like cone?
Yeah, it's just a cone. Yeah. All right, see what you can do with this one, and then we'll work through it together. All right, let's make sure you guys have all got it set up reasonably correctly. So first off, we've got a cone, and it says the point of that cone is down, right? Standing point down. And we know that the height of this cone is 10. Is that height right there changing of the big cone that is the tank?
No.
No, so that's 10. And what about the radius of the big cone here? That is 5, and that's also not changing, right? And then what we have is we have water filling up through the tank, right, at some point, right? We've got a cone of water within the cone. And we want to know how fast the water level is rising. So how is the depth of this changing when this height is 6? So is this 6 right here changing as we fill the tank?
No.
Should be, right? I mean, as I start filling this tank, it increases up to 6 and then past 6, right? We want to know exactly how fast the water level is rising when it's exactly 6 feet. But the height right here is changing in the context of the problem. We're filling it up with water, we're pouring water into it, and this water level is just constantly going up. If we're constantly pouring the water in, this water level is constantly increasing the entire time. True? We'll call that H. That height is changing. What about the radius of the little cone of water? Is that changing? Down here, it's smaller than it is up here. So that radius is also changing as we pour water in. And we want to know how fast is the water level rising, which is a dH dt value. So we're looking for dH dt. And are we given a rate of change of anything in this problem?
9 feet cubed per minute.
Yeah, we're given water is flowing into it at 9 cubic feet per minute. And so that would be a change in what? Should be a change in the volume, which we should be clued into because it's 9 cubic feet per minute, right? So it's flowing into it, it's increasing, the volume is getting greater, so that's a positive 9. And so we need to find a way to relate volume to height. So to start doing that, just right off the bat, what's the formula for the volume of a cone?
1/3.
1/3 base
squared,
height.
8.
1/3, the area of the base, pi r squared times the height. And the issue we have come across now is that we have v, which is fine because we have how it's changing. And we have h, which is fine because we have how it's changing, or we're looking for how it's changing. But we also have an r in here. And we have no information about the radius of the water, the cone of water, or how that radius is changing. So we need to find a way to relate r and h together, kind of like we did in optimization problems, right? So that we can write it all in terms of just one variable. In this case, we'd like it all to be in terms of h. So how can we relate r to h?
Well, the ratio between r and h is always the same. So we know that the radius is always half of the height.
All right, yeah. So, and we know that because these both share a right angle and they both share this other angle. And 2 angles indicates that the triangles are similar, right? If you have 2 angles that are congruent, the 2 triangles are similar triangles. And so the ratio from 5 to 10 should be the same as the ratio from r to h on this other cone. And if we were to solve for r, we would get r is equal to 1/2 h. And we should then be able to take that, plug it in, and get volume equals 1/3 pi times 1/2 h squared times h. Or simplified down, volume is 1/12 pi h cubed. Good or no? Yeah, no, maybe. All right, so now we've gone through our steps. We've understood the problem. We drew a picture. We wrote an equation. Now we need to differentiate each side with respect to time. So that will give us on the left just dv dt, and on the right 3/12 of 1/4 pi h squared dh dt. And looks like we'll need another page here to plug this all in. dv dt was what?
9.
9. So we're going to have 9 equals 1/4 pi times our height squared. Well, our height that we were interested in was h equals 6, right? So if h is 6, that ought to be 6 squared, and then we have dh dt. So we're looking for dh dt. So we will solve for dh dt. We'll multiply by the 4. 36 equals 36 pi dH/dt, or dH/dt equals 1 over pi, and I think this was in feet per minute. Yeah, feet per minute. Good or no?
Good.
All right, cool. That's the basic idea behind related rate problems. That's it. That's all we're actually going to do today. So we have about 30 minutes left. I think this would be a good time for you guys to work on the optimization and related rate problems that I posted that are due. When are they due? Are they due tomorrow? Did I put tomorrow as the due date?
Yeah, it's due tomorrow.
Yeah, so I think this would be a good time to not procrastinate and work on those for a while. What do you all think?
That sounds like a good idea.
All right, wonderful. That will be our plan then.